Hello and welcome back to section 2.4 on shortest distances and closest points. In this video we're going to do 2.4.3, the distance from a point to a plane. So here we are going to be given a point A, x0, y0, z0, and a plane pi, ax plus by plus cz plus d equals 0. We're going to find a formula for the minimum distance, the distance from A to pi, and then we're also going to find the closest point on pi to A, and we're going to call that point Q. So first we're going to do a formula for just the plane distance, if that's all we need, and then further down we are going to do a procedure to find Q, the closest point to this given point A, closest point on pi to A. So let's go with this distance formula. So we are going to, first of all, choose any point P, x, y, z, that's in the plane, in pi. And so let's go ahead and draw that point maybe here, P, and then we can construct the vector from P to A, or the vector PA. Now, if I take my normal vector, this normal vector here, I can redraw it anywhere I wish, and so for the sake of my diagram, I'm going to redraw my normal vector there. Now, the distance, the blue line that we're looking for, this is, right, the length of this blue line here, that is a minimum distance, and so it is a perpendicular distance. Well, the normal vector is perpendicular as well, but the normal vector may not be the correct length. It's in the correct direction, but may not be the correct length. And so what we've done in previous situations for that is to scale it. And how are we going to scale it? Well, I'm glad you asked. We are going to take our vector PA and we are going to project it over. And you can see here, so my vector in red is going to be the projection of PA onto the normal vector. And so that is going to scale the normal vector so that it is the same length as the distance that we are looking for. And that means that the distance from our point A to our plane pi is going to be exactly, it's going to be the norm of that projection vector. So the norm of the projection of PA onto N. And that's kind of it. But we can go through and simplify that a lot to give the standard distance formula that is well known from a point to a plane. So let's first of all write our projection in terms of the projection formula. So that's PA dotted with N over the norm of N. All of that times vector N, and of course we want the norm of that. Now we're going to use a property of vectors that you should remember from your vector unit, and that is when I have the norm of a scalar times a vector, that is equal to the magnitude of the scalar times the norm of the vector. In other words, it looks like we can bring the k outside in absolute value. Well, this is a scalar right here. That is playing the role of k. So we can imagine bringing that outside of the norm, but to do so we have to do it in absolute value. Oops, I forgot a square in the denominator. And incidentally, that is one of the most common mistakes in the projection formula, so let's pretend that I did that on purpose to have a pedagogical moment with you. So when I bring that outside, I need to do so in absolute value. The norm squared is already positive in the denominator, so I can apply the absolute value just to the dot product in the numerator. So PA dotted with N over the norm of N squared. And what's left is the magnitude of the vector that's inside, so the magnitude of N. So that's very nice because this square and this norm will cancel out. So we end up by having the absolute value of PA dotted with n divided by the norm of n. So we can go a little bit further even. We know that A is a given point, which is x0, y0, z0. P was our point that satisfied the equation of the plane, so it was x, y, z. So we can write this as the vector PA, so the absolute value of PA is going to be x0 minus x, y0 minus y, z0 minus z, dotted with ABC, and that is going to be divided by the norm of n, so a squared plus b squared plus c squared under the root. So if we expand the dot product, we're going to have in absolute value a times, and let me distribute the a at the same time, so a times x0 minus ax plus b y0 minus by plus c z0 minus cz in absolute value, and divided by the square root of a squared plus b squared plus c squared. Now that looks like a bit of a monstrosity in the numerator. We can clean that up even more. So if we have here, right, our point P was the point x, y, and z, and if it's in the plane, it satisfies ax plus by plus cz plus d equals 0. Well, if we keep d on one side and move everything else over, minus ax minus by minus cz is equal to d, and look at that. Minus ax minus by minus cz. So we can replace all of those things by d, which means that we are going to have ax0 plus by0 plus cz0 plus d in absolute value over the square root of a squared plus b squared plus c squared. And that is the standard form of the distance formula from a point A to a plane pi given in its general equation form. So one thing to remark here, it kind of looks like, and this is not at all what's sort of really going on, but it kind of looks like we took A and plugged it into the plane equation, right? It looks like we plugged it in to the plane equation and then did some stuff in absolute value and divided by some stuff. And that's just kind of a way to maybe remember that that formula, what it looks like. But it is absolutely comes from projections and simplification. So that's the standard distance formula from a point to a plane. Now, closest point. What if we don't want just that distance, but we also want this point Q? We want the point in the plane that is closest to A. Well, actually, it turns out that what we did above is, it's kind of useful. So let's recopy what we have up here, and we'll bring that down here. And so if we take a look at our same diagram, so our same point P that is chosen and our same projection, we want to find this point Q. Well, there's a couple of ways of doing it given this diagram. The first is if I fill in the rest of the traditional projection picture, then this vector in green becomes the orthogonal component of PA relative to the normal vector, and that just so happens to be the vector PQ. And so one way to find point Q, right, if we want the position vector of OQ, well, that is the position vector of POP plus PQ, but PQ we just said is the orthogonal, so OP plus the orthogonal of PA relative to N. So that is one way of finding the position vector of Q. Or another way of doing it is, well, just look at that projection vector. If I reverse that projection vector, right, that's minus the projection of PA onto N. That's also fine. So another way of doing this is, well, I can say OQ is OA plus AQ, and AQ is minus the projection of PA onto N. So that gives us a little procedure, right? The first thing that you need to do is choose a point P in pi, any point P in pi. And then the second thing you need to do is either use the orthogonal or the projection to find the coordinates of Q. And then obviously, if you have the point Q already from some other calculation or what have you, you can find the distance from point A to the plane pi. Well, it's the norm of that vector QA or AQ, or the norm of the projection, which is exactly where the distance formula came from. But if you have the point Q already from some previous calculation, you can just take the norm of that vector to give you the distance from the point A to the plane.